you all again for now the second session. Your Holiness, you will probably remember Anton Zeilinger from your time with him 10 years ago here in this room, but also in Innsbruck, where you tried to see an atom, but had the unfortunate karma not to see it, I think you say in your
Yes.
Anton is now working at the University of Vienna, where he and his research group in the foundations of quantum mechanics are doing some of the most important experiments in the area of quantum physics and the new area of quantum information and quantum computation. So it's wonderful to have him back to work again with you on some of these foundational questions. I'm not going to say anything more because we're going to launch right into the science. Anton, the floor is yours.
Thank you. Well, it's a great pleasure to be here again, and a great privilege. After our two meetings, one was 10 years ago here, and the other one was 9 years ago in Innsbruck. Right? Now, since that time, you might ask whether everything is the same or whether something has changed in quantum physics. And there are actually two important changes, which I would like to report to you during our discussion. One change concerns a technical thing happening, and I know that Your Holiness, you love technology, so I will mention that. And that is the fact that based on these fundamental questions, which we discussed already, people are developing a new technology for information. And that is really a big surprise. It often happened in the history of science that the really big changes came from research which was not done for a purpose, just out of curiosity. This is happening here again. And the second new thing...
Mixed purpose marriage. That's real unbiased research.
Unbiased research, right?
Really unbiased.
Right, yes.
Yeah, that's I often use it telling Buddhist, once we fixed some goal, then try to prove that it's actually biased.
And I agree, and it sometimes can be the wrong goal.
That wrong goal, the right goal,
because rightness or wrongness is something that we can only decide later on.
Afterwards, yeah, that's the problem. Yeah.
What implication?
Right.
We find something with open mind. Right. Then the second thought was, from another viewpoint, now what benefit?
Right, exactly. Yeah.
Okay.
I agree, yes. That's exactly my viewpoint also. Now, the second point which happened, which was actually in part encouraged, if not inspired by our earlier discussion, is some new ideas which we are developing on the conceptual foundations of quantum mechanics. And these are ideas according to which...
quantum kita kanda jeba jidang samtandante ta kotana quantum ticket kuran ngotong jeba experiment worba experiment dobe ta deshe jabdang conceptual, more of an explanation how to explain the phenomena.
Why is the world so strange? Why do we have quantum mechanics? And the approach, I will talk later more, but just now in kind of terms of a small overview, is that we are simply asking, maybe knowledge is as fundamental or maybe even more fundamental than reality. I will expose that. I will expose that in some more detail later on. But before material reality.
Yeah. More fundamental than a material reality.
로데. 다시 제일 되시 중에서. No.
But as I said, this will come later, and I suggest we just start reminding us of a little bit of some of the issues which we discussed and which are essential for discussing quantum physics. So.
삼다나 사반이제 다간다 지 반응을 유랑소 되베 유고 샤마도나 아니 직샤는 샤고 버봐 다 샤단 달로고는 파샤나 마도 샤서 매버지 근데 그 삼버지 레샤강 다 제일 쉬워서.
So here on the first picture we see the famous double slit experiment. The one which I actually showed 10 years ago in reality here. Remember, I had put it up with lasers here on the desk. And this is kind of a essential experiment which has been done in reality also many times, which shows you or shows us some of the fundamental problems. Now, we can quickly go through the phenomena which we observe, and the phenomena you observe is basically very simple. You have some light, say, but it could be something else, coming from the left, going through this first slit, and then it passes through this second screen, which has two slits. And then back there we have, when both slits are open, we find that there are dark and bright stripes. And if we don't know anything about quantum physics, then this is a phenomenon which can easily be understood. So without quantum physics, it's very simple, because we know that light is a wave. A wave goes through the two slits, and back on this final screen you have what the two waves add up, which came through the two slits, and at some points the two waves add each other, so the light is strong there, is bright. At some other points the waves extinguish each other, and the light and is dark. Cancel each other, and it's dark. So that's easy. But unfortunately, in 1905, a young physicist called Albert Einstein discovered, he was very young at that time, 26, discovered that light is made of individual particles. Now the question, how do you reconcile this phenomenon with the idea of particles, of individual particles? Individual particles.
Yes, particles,
right. In particular, if you now just think about this experiment here, and if you consider an individual particle, then one would classically say that the individual particle can only go through either the upper or the lower slit, which is fine. And then it goes back to the observation screen, and you collect it somewhere. Then the problem is that if you do this experiment with many individual particles, one after the other, you collect them on this observation screen, then if you have many, you see the dark and bright stripes. Which simply means that each particle knows that both slits are open.
Particle the 기분이가 제발
yes.
심해서지. 근데 그다가 뭔가 좀 개론이 깨지 봐. 이 뭔가 그거로 나지기나 지금도는 지나만 줘 잡아 봐. 다든지 비게 좀
맞아서서 니 말배.
but
뒤처럼 뭔 거요.
뒤처럼 딴 거로 봐. 딴 거면서 기군이 제자요나. 네가 제자요나.
알아 되는 거 유튜브 찍으래.
당주르르만 당고 말해.
알래.
당주르르만 당겨 말해. 당매인자 고단 뒤랑근랑 신내 대요나. 비기
찍으는 실내요나.
찍으는 신내요나. 비기 잘려야 스크린 대간데 아니
니 봐요.
랍그 디 소년 텐도 말와. 오늘은 진짜고 르르 당겨 되고 뒤에나 고 비기 밥서 질이야. 디 낙디를 잡셔 그러마도 랍그랑 신들 리메 봐. 대통령 게
So the question then is, how does each particle, which has to go through either this upper slit or the lower one, know that the other one is open? Because each particle knows that it must not go to the dark places. Okay? Now this is a puzzle.
저는 보통 왜 당스라고 말해. 왜 두면 뒤두면 되대가 말해.
말이 땅도 particle 좀 당거래.
네.
Photons. Is it photons or electrons?
Photons. If you want, you can photons. You can have electrons.
But you send one at a time.
One at a time.
Yeah.
One at a time.
But many. You get the pattern when you send many.
Many.
Yeah, you get one. You send it. It lands somewhere. You can take a second one. It lands somewhere. Third one. It lands somewhere. And after some time, you see the pattern slowly coming up.
Oh, really? After some time, you see the pattern come. Then 림싱이 된 pattern 지 용그래. 찍찍땅땅땅 되니 림싱이 된 pattern 용그래.
Right.
Interference pattern.
Now the question is, if you have if you assume, which is a pre-quantum view, that each particle takes a path, even if you don't know it, then you have a problem. Because, as I said, how does it know whether the other slit is open or not?
Did you explain that? It has to know the slit is...
기훈이가 제자야나. 근데 되게 particle 땅배 갑래야. 그 되게 네가 제보다 신배 소리 치는 남주피가 통교를 해서 나온. 그래.
그래서 나디 나보다 조조 말해. 그러나 카르보인 비 사치텔에 조고로 봐. 그래서
가고 결로돼.
그래 결로돼.
스크린 담아들어.
그래.
그래서 개고 오메 개군데를 조나트는 나보다 가고로 봐. 그래서 대 서브 인터미디ate 땡기 개군데를 조고를
알레 뒤처럼 되기 가.
말해. You want to clarify this?
So the particles, when they're going, when you say they need to know that both windows are open, it's that the particle that as you send one particle and another particle, another particle, another particle, eventually an interference pattern, white, black,
exactly,
comes up.
Right.
So if you send the particle through and it goes through the lower window, for example, it might hit the black one.
Right.
So it can't go through the lower window. It has to know that it needs to go only through the upper window.
No.
No.
I mean, it turns out.
Why did it have to have? Why do you say? Go ahead.
To make logical sense, you have to say it went through both.
The point is, if I close one of the two slits, it doesn't matter whether I close the upper one or the lower one. No stripes appear.
Okay.
But you said it has to not hit the black part.
And if I open both slits, it never hits the black part.
두면 뒤에 말해. 두면 뒤에 럽디 처럼 두면 속옷이 처음 말해. 속옷이 처음 말해. 사진 처음 말해. 이렇게 말해.
So this is important. We have to get the phenomenology right before we can talk about the meaning.
Yeah, you should ask that.
What?
You can come in. Use the
microphone.
Use the microphone.
turn it on. Is it on now? Suppose one of those two, we're talking about the middle vertical plate there. Close one of those slits. Then when you send particles through, there is no pattern that appears.
Yes, we close this, and there's no pattern.
There's no pattern.
Well,
now open it. Now open it. Let me just finish. Now open it.
Now
Any
we open
individual particle goes through only one slit, so it shouldn't matter that the other slit has been opened, and yet it does matter.
it. That's a good way to argue, yeah?
다 조라면 돼. 그러지. 그래서
Tati nyoro samshin taisana tantugal photon rema tangyo marwa. Tantugal photon rema tang mabi za gigun chik cheba da ni ma cheba ni cheba ni ngun ran jine keba yonggo yo mares.
그러지. 알레. 다 우슬네.
keba yonggo yo mares. Ta gigun chik chibu che shabena pige gap de number buti lap ke number bu tengu do. Ti tengu yo mare. Kanda we tigro chik ma tengu yo mares. 기운이 셔셔두가라 아니 대그 패턴 통교레스 디엔자 신문을 하는 지금은 기본직 제보더니 마치 이 제보니 버를 개발 통과예요 말로 와서 로스 찍는 누구였나
I don't know. Okay.
So how do you interpret this? Yeah.
Well, the modern way to interpret this is that if we are not allowed to talk about the path a particle takes unless we really measure that path. We are not allowed to talk about anything happening, any phenomenon, if it's not observed. This is the Boer quote I wrote down here. No phenomenon is a phenomenon unless it is an observed phenomenon. Yeah. So we are not allowed to assign a path.
안데 페노메나 로지전 지단하는 지단샤비 나 세르고 있으면 지단샤비는 패지 페노메나 소전에 패지 통은주 뒤조지 마다. 그래서 통은주 집이는 그 유유전 제지도 쓰고 말이지 얘네 통은주디 여덟 메시아디 진진직으로 이미 그렇다 다 전마다.
나린.
문제게.
나린. From the Buddhist point of view, as we listen to the scientific presentation, much of the language of phenomena that you're using, from the Buddhist point of view, it would be at the level of what we call the evident phenomena. So with regard to evident or observed phenomena, then it makes no sense to talk about phenomena that is independent of the observation.
So it sounds as if we agree here on a point.
또 고주도 시도 고주지 여러 번 그냥 치버려 봐. 그래서 안 되지. 그때지 그래.
Right.
변호지 변호 원부시에 변호 그게 주기야지 이번이나 때 여덟 명씩 타자 예매사디 코라 진지글로 예매 코라 타는 모두 패시셔야 될 거도 가. 그 다시잖아 할람 디 텐지 민이 소르지. 다이네 그 자식들도 쓰고 말아. 다니지들도 쓰고 말이지. 이네 그 통주 집에 있나? 그 통해 주요나? 디 요리스타 자다. 마도 거지 똑배 쳐봐지는 시합하면 그렇지.
So with regard
to 왜? 근데
세례법이 빠진 망체도 되지 지난 송도. 네 레버가 그나 아니 가도 유크롬은 빠지 요 말했어. 마도 그런 아니 가르쳐 그래. 레버가 빠
타냐 따라서.
마도 근데 유크롬 중에 레버 좀 요 말에 그래서 메시
야. 제사가 아들 되기 싫어서 유진 타냐고 한 게. 여보 마도. 그다 다 돈은 유진원에 좀 매도 봐. 내가 저 떡배 관계 여보세요. 그거 따다로 되는시도.
So His Holiness is wondering where the actual the crux of the matter here is, or whether it is on the question of phenomena itself, or whether we are talking about the reality of the phenomena, existence of the phenomena. So with regard to the existence of phenomena, we can only make sense with respect to an observing subject or observation, then we can talk about whether it exists or it does not exist.
Anton, can I
come in? Yeah, sure.
And Matthew also.
Matthew?
This morning, to go on this example of a glass of water, that there is no phenomena without being observed phenomena. Actually, the classical example that John was giving of the same glass being perceived differently by different types of consciousness according to their own structure, like as pus or as water, or for a fish as its habitat. And so the idea is that the question, would there be a phenomena without an observer? Is there a common ground, an object that is totally independent of me or an hungry ghost or an animal or a fish seeing it, that exists on its own and we all see in different ways? But the issue you raised was more to say that there are phenomena that comes in relation. The set of phenomena that meets the consciousness is not yet a glass of water, it's not yes, past, but the fact of meeting of the consciousness that observes a particular type of consciousness with a particular set of phenomena, it crystallizes a particular appearance that is water for us, or that might be a different, like nectar for the gods. But this is a unique phenomena because of the relation of a particular consciousness with another set of interdependent phenomena. So is that something similar?
I actually think there's another issue.
I don't think so.
Yeah, I think we're getting sidetracked. Really, I think it has to do with evidence and what you can infer from the evidence. So you had valid inference. Right? Yeah. So you have two different phenomena, if you will, two different observed effects. If you close one slit and you let light come through the slit that's open, then you see one form. Yeah? All the particles of light land here, and you think, okay, on the basis of this phenomenon, I infer the existence of a trajectory and a particle that's following that trajectory. All right, so that's one valid inference. So one reasons from the evidence to a kind of hypothesis about the nature of light. Then you take a second experiment with two slits and you get a very different result, which leads you to infer not particles but waves. And these are in contradiction to one another.
타기 남주르부터리야 particle 남주모 등면자 근데 particle 켜줘요지 particle 뭐요부터 다 기운이 쳐셔도 이거 비게 랍그 넘버 등교한자 다한테 랍그 넘버티 모동기 주베 들어봐 대실샤제 아니
니가 뭐도 말해
이제 니가 뭐노래 다이네 그 보인도가 랍그랑시 뭐 보야다 두그랑시 뭐 보야디 그 무슨 영화지 실내샤지 보고 걸어와 다 보도가라 기운이
그걸 두그랑시 인수는 가야래
그래 so I mean can't we just can't we just say that the wave itself is composed of particles?
Anton, you want to try to deal with that? I mean, that's an interesting hypothesis which has been tried out.
What quantum mechanics?
Because light is physical. It's a matter, part of the matter.
Well, that's also a subtle question. Do you want to?
Well, that's a lot of questions now.
담시야 콘수한테 웨이브 사지다 가서 웨이브사도 가가다 가가 면로
light 세들로
삼삼다나
아도 웨이브 사지
웨이브스 랍
달럽다 웨니 가래 가가래 가래
나도 웨리아 두그란신다 랍그란신이가 열슬라고 그러지
any these are non-good
은 군인 남그 개바 임바질이야 시질에 네가 총년 지시고 다든지 뭔게 지르고도 쓰듯 그지도 말래고
If, for example, you ask about
웨이브스를 저는 다 보지 연구식에 줘 봐.
조직단나 웨이브래. 양 신반이단나 양 그런.
제 연구로다. 제 러브 타니다나.
군이양 간다래도.
뭐 오직 산주로. 더 못하래.
So, His Holiness is, in the
근데
Buddhist...
뭐를 더 못하랬어야 디 시우장 캠을서. 디 여천에 여천이야. 똑배 가서 그러다. 똑배 유진진다다. 무슨 도움이 유진진다다 캐스트와.
One of the epistemological concepts that in Buddhist philosophy that is used is the idea of single nature, different identity, or distinct, or how do you call it?
Essentially
nature,
identical,
and
conceptually
distinct. Essentially identical.
Essentially identical, but
conceptually distinct. So can't be, and also that takes into account the different modes of engagement of sensory perceptions on the one hand, and conceptual thoughts on the other.
Or
interpretations, because thoughts are understood to operate by means of selection, whereas perceptions tend to be more kind of, immediate and direct.
다음에 다 가서면 안 되더라 그 가서 그래. 다 주는 거고 말다. 그러나 똑배 어리스 뒤리스. 봐. 그게 뭐 잘해서 고치거라.
So in the example here, although this is just a kind of a speculative thinking, example to use this kind of idea here would be to say at the conceptual level, you can interpret it as particle or as waves, which are then they are conceptually distinct, but experientially, which is perceptually, you can have the experience of the phenomenon
of light.
Well, that's very good because what we, if I may say so, because.
But it could be also kind of a slight kind of, how do you say,
research.
Facile explanation.
Kind of a trick.
A trick.
It could be seen as a trick as well.
What is really primary to me? Now we are already deep in the discussion. But what is really primary is what we call in quantum physics the individual event. Like if I, for example, if I put here in the observation plane a detector.
Detector,
yes.
Like this here. Okay, this is a photon detector.
Oh yes.
You remember?
Yes, I did. Yes. Same machine.
All right. What happens is when light comes in here, you know that, but I have to explain to the audience.
Yes.
When light comes in here, this light actually is very attenuated. It is made weaker by effect of million because there is a lot of light here.
Yes.
Okay. There is lots of light. Yeah, they should.
Okay. Yes.
So there's an opening here. There's an opening here where light comes in, and then in there is a little device which changes an individual photon into an electrical pulse. What happens is that the photon kicks out an electric charge, out of a metal plate, and that is then that gives rise to an electrical pulse. And the electrical pulse travels along here, and in here is a little speaker, a loudspeaker. This microphone doesn't really work.
This microphone here,
Oh, this is not very loud.
No. Testing 1, 2, 3. Yeah, that works, but it's not designed very well for that.
No, the microphone is not very good.
And that's it.
Now it's better. Now each of these clicks is a photon. If I hold it towards you, not so much light. Right. If I hold it to the screen here, up there to the lamp is more light. Okay. So, but the point I want to make is what we really have as the primary thing. I don't want to use a name actually. We talk about is this click in the detector. And that's all we have in quantum experiments. We have these individual clicks. If I would put my detector in the observation plane where you see the dark and bright stripes, you would get many clicks when you happen to hold it in a bright stripe. You get no clicks when it's in the dark stripe. So we have these clicks, which is the primary thing. And on that, we now build our concepts. But we don't need to build the concepts. In principle, we could just talk about the clicks, but then we would have very little understanding. Okay.
Conceptual level that quantum mechanics now cage na musum trube then to
Now, one question.
The density 때문에 density tar 또 윤도 영어로 또 그래서 그 지발 롱기었어. 그 태그를 쓰신 거 말고. 딱고 김재권으로 가시다. 이 김재인되게 tar 또 윤도 영어로 또는 말로 그렇습니다. 그래서 안 나가지고 보러.
So there's a similar epistemological standpoint in Buddhism where strong emphasis is placed on experience or observed phenomenon as the kind of the final the end, final arbiter.
The end of a chain of inferences has to end in perception.
So although much of our knowledge may be derived on the basis of inference, but inference depends upon certain observed phenomena. So therefore, the chain of inference is sometimes compared to kind of a process of blind leading the blind. And ultimately, it has to be led by someone who sees. So the experience is like the person with the sight, and the chain of inference is built on this. So it has to ultimately... so this seems to be the same pattern here.
And do you also have in Buddhism this idea which we have in science, and that is that the chain of inference not only has to work along in one direction, but it has to be a closed loop. It has to be self-consistent. So what you used to explain might actually explain the starting point also. Has that been discussed in this? Because this is something we use in discussion sometimes.
You want to give an example?
Self-consistent interpretation. Well, it's what I refer to is, well, now we are getting into very deep material. What I refer to is the meaning circuit of Wheeler, you know? This kind of this question that you have the primary quantum phenomenon, and that you interpret it as you use apparatus, you interpret it as an observer, but in the end you yourself also consist of quantum phenomena. And so you yourself as an observer has to be consistent with what you explain in terms of quantum in terms of the phenomena to begin with. You see?
Musum shilashaje ni jeba tensi ta gyugurwa the poet ta poet gyugu into gala ta thar musum thugu yorba tena shi ya jeba gyubati jite khona so nam penju chachangro shi ta penju kanda chigchil menge wachita tete chugu yorba ta korbo no chugu eternally ta ine khona main point thing kushran gocho maso. So Anton, is the question that not only should the chain of inference be ultimately grounded in experience, but also the chain within themselves should be consistent, self-consistent?
Yes. It should be both. It should be kind of... It should never contradict experience. Absolutely.
That's fine.
Absolutely. So another question I have about what I just learned.
So His Holiness is interested in still trying to... So I was bringing up. Maybe this has something to do with the
다음에 가서 지사님한테 뒤처럼래 아니 러브레스라나
나름.
다디
니가 있었군요.
지당 모습도 다 됐어. 당연히 해야 돼.
나름.
꼭 응신이잖아. 그 러브리. 응신이잖아. 러브 코레 뒤참을 두대 이르잖아. 코레 뒤참을 응시 되게 하래. 그 러브를 응시 되게 하래. 딱 가셔서 안 돼.
되는 그런
그럼 뭐지 제. 다 탄연이 제식으로다.
콘서트는 마신 랍다.
다 뒤뒤로세. 딱 뭔가도 걸려. 다.
랍단 뒤니 되게 어려워. 콘서트에나. 랍단 뒤니 게어 인자 다 지기는 지만 미.
저 대번 얘기 왔어 가지고.
나를.
뭐지셔로.
So His Holiness is, we were kind of discussing, because His Holiness was saying that if we use this Buddhist epistemological concept of essentially identical and conceptually distinct and apply this to this wave-particle duality, will that, because I was suggesting another way of interpreting this would be to say here the law of the excluded middle breaks down. But His Holiness was saying that if we apply this idea of essentially identical and conceptually distinct, then we don't need to break the law of the excluded middle.
I would also not have the law of the excluded middle breakdown. This, the point which we in quantum mechanics say, and that is now something I would like to hear whether it has parallels in Buddhism. I have this essential phenomenon, which is the click in the detector. And then I can do two different experiments. We have been talking about that. In one experiment where both slits are open, I can use the phenomenon of wave to explain it. In the concept of wave. In the other one, where only one slit is open, I use the concept of particle. But then what we say then in quantum physics is that the two concepts exclude each other, because the two different experiments exclude each other. The slit cannot be open and closed at the same time. Now, is this also a notion in Buddhist concepts when you talk about the essential thing and then the conceptual level, that you have conceptual level which actually cannot hold at the same time, and you have to make a choice which one you accept on the basis of the essential basis, because this is really important in quantum mechanics.
대시지 잡으나 베는 기군 직체베나 durgunam jutun korwa giguni chebena labgunam jutun korwa tungyu da kunini bote ngo togo tate inza togbengoene jedan tate duyorwa kuranzu chebena labdan duini bote nange nambi게 시드메바 지기요 찬스 인자 니네 디교요 말에 해서는 디 제바 체게 고카가 잡으랬어 그래서는 찍
뒤쪽을 말해
durgunam jut은데 기군 직체는 충분히 봤어 라고 주토에디 기군이 전 중보인자 제변 권면다고 돈에
뒤용고
도배디 가가 연구 연자스
뒤용고게 탄해 주시던 터도 주시던 그 주시 메다이 인자네
나를 때네
권예도 메다샤
대만 이걸로 질이야 샤거로 냠샤 디가사 다마시야
산제살에 아다 디디베다 다 산제살에 가서 마티요 선체
마르테 도배 디 대니 진짜도 도배 또 두고 있으려고
똑배 지금.
His Holiness was saying.
그 뒤도 뭐 싸니 말왜? 알레. And do you tell me to go 균 소리고 그래서 이런 걸 그러셔. 네. 배경이 되죠. 그니 저도 왜 앉아있다.
Can't we say that this is an evidence of this devoid of intrinsic existence? That the phenomena, whatever it is neither intrinsically a wave nor intrinsically a particle, and therefore, because of being devoid of intrinsic existence, it can appear in different ways under different conditions.
Well, I think the issue is...
His Holiness was saying that, in a sense, there is a parallel. For example, like we talk about the two levels of truth, and the two levels of truths are essentially identical and conceptually distinct, and they are also thought to be mutually exclusive. No, they obey the law of the excluded middle as well. So, in a sense, there is a sort of a parallel here. So, the perspective you adopt, if you approach the phenomena from the ultimate perspective, then you have one understanding. If you approach the phenomena from the conventionally truth perspective, you have another understanding. So there seems to be parallel here.
There's a...
the Kuranda Tonga Martadi.
저다 고 뭐부지 그 남주로 지당으로 면자지 예배 뭐네 그랬어. 야, 그 지당 면자지 뭐네 가서 저거 말이지 가서다 뒤처리를 했어. 너 통화를 해. 뭐부지 가 간다 왜 그럽사디 요하지 봐. 그 디네 치 델 송사지 종시에 동거래. 종시에는 그 수신이 타죠.
For example, in the case of wave, the perspective of the wave, because we can talk about it going from this opening and being kind of detected on the other. There is a motion.
Right, we talk, yeah.
There's a motion.
I would like a translation.
There's a lot of discussion. Part of the discussion is that
I love this. I would like to know what the translation.
Ladola was pointing out that if the phenomena is an observed phenomenon, then it has no relevance to the conceptual distinction we are making. Because when we say conceptual distinction, we are talking about a level of distinction not at the phenomena level, conceptual, the interpretation level.
That's behind the picture, yeah.
But I was saying that what is observed is not the wave, but the effect of the wave. What is observed is not the particle, effect of the particle.
Right.
And the other
so
question
we are not observing particles.
A lot of the discussion here is also what exactly is the distinction between a wave and a particle, Anton?
Why don't we summarize and move on to the next topic?
Anton, part of the question here is also what exactly is the distinction between a wave and a particle, and why is that incompatible?
Well, to us physicists, the distinction between a wave and a particle is that the particle is localized. It's here or there or there. And the wave is delocalized.
Yeah.
The wave is all over the place.
Yeah.
And therefore, we physicists see a contradiction between the two concepts. You can only have this one or this one.
어다 되기지.
간다 유고서 개념이 네버 찍고 두고
챕터에 참여 주고 말아.
나래다 참여 찍고도 뭐 대내고 내 타지도 돼요 그래서 두고요 말고 딱고 사제 가로질이야.
그 챕터에는 대야래 대야면서 두고 말아.
나래 now. But there's a kind of a localization to the wave too, because you have a certain circumscribed
Exactly.
space.
Exactly.
그 챕터에는
Sure.
Yeah.
and 그 챕터에는 드는 대 송스로 두고 말아.
Then in that case, how can you explain the motion from one place to another?
I mean, in physics, what we talk about is wave packets. Like when you throw a stone in the pond, then you see a wave propagating away, which is locally a wave packet. It's there, and then it's there, and then it's there. But it's much less local.
Wave in wave Quran.
다다 왜 아다 왜 받을 겁지서야 돼. 들어 라이트를 쓰고 봐야 돼. 저 라이트 거는 저도 말해.
But light ramare. The light Quran이야 proper particle the 니가 찍으로. 다 light 투몽 치우듯이.
But same is light.
진짜한다. 안다 그 콘솔 안다 지 들어서다. 그 샤즈디 뒤니리스. 뒤직디 크둘치. 뒤 뒤기 차듯이. 뒤기 치래요체. 더 찍디도서 야마도시. 그걸로 붙이래요. 저 뒤소소면 저래. 나도 뒤직을 받았어야 돼.
나는 뒤직을.
So they also has a comment back in the
어르바. 어르바. 저 두 분이 차배 차네. 웰러리스. 그봐. 그게 퍼야 돼. 내직을 보고 가래.
근데 기본적 체는 내직을 보고. 니 체는 랍나 시체는 니가 루지도 거. 그때 요거 된 거래. 니 체는
저다 측이나 잡아 있나? 전에 봐 찍다 말아 봐. 딱고 도머리 찍으랬어 봐 있나?
that 요거 된 거라. So you are sending one photon at a time, okay?
Yes.
Now
really one, but every minute one.
Yeah.
Yes.
So
really
when
one.
you have both slits open, so then the question is, when it hits the detector screen, is it being hit as one or two?
It's hit at one place.
Yeah, one place.
One place.
Yeah.
Even with both slits open.
Yeah.
Yeah.
It's one very
Yeah.
small.
just
Narisha. But in that
So
case,
it's a
how do you get the wave pattern?
If I collect many, I get one here.
Yeah.
I get one there. I
Okay.
get one there.
카시다 뭐 있나?
And I collect.
카시다 뭐
망고
있나?
땅이나 아니.
얘는 카시 열었을 때 카시 뭐 욕으로다.
Okay.
So Solons is saying in that case, what's the problem? Because they're kind of randomly picking up space, and then you get this pattern.
They're
Yeah.
picking up
Well,
space.
randomly it hits.
That's an interesting expression.
They're randomly arriving, which is true.
Yeah.
And this is part of the mystery of it, that there's a randomness to the arrival. You can't predict where any one of the
근데
photons
가봐도 막
arrives.
봤어요.
But the
턱선이.
pattern is whole. But you on
띵임이
average you get a pattern.
That's actually to us a mystery. That within the pattern there's randomness. The
랜덤
particle
yes.
can show up wherever it wants.
that's right.
But if I collect many, I get the pattern.
Pattern. So the individual event seems random, but the overall pattern emerges from many events. So the many carries.
그 따위나 아니 random 더블체 게임에 더블체 다 망부시 땅베나 아니 야 고지 pattern tongu도 wave pattern
애기군이 제비.
기분이 지.
안다 왜 패턴 사디 파 송의 겁을 다 송스 좀 저의 겁을 쓰게 하래. 이거 파 참스.
포탄.
세상은 더 단데 재미도 봐요.
Because what is being observed here, to clarify, is really the effect.
다 숨진이도 숨지도 두 번이도 쓰고 땅에서
What is being observed
pattern,
here is only the effect
Of the light.
that is registered on the screen.
It's the detector click.
Yeah, detector
And
click.
the rest we infer. We infer that there was light. We infer that there is a laser. And so this is all inference.
What's
What's really happening is the click.
이게 스크린 강이야. 이거부터 다가 비기 가이가
지사다 너네 봐 어디 침백해도 럽긴 남발을 침백다. 아니
되게 좀 말해.
되게 남발 침백 쓰고 말았다.
쓰고.
어디 멤버체. 디마베체 답게 포차를 제라
나래
아니 그 넘줄디
라고 남주다
딜라고 넘줄 그래서 그래
딱한 망부탄 되고 라고 남주 된 것도 그래 되게 옆에 밴드 까본 나고 그 용해야래야 라브르지 있는 맛도 된 거 말아 카시마다 마담배는 줄고 남바데
대인지
딱 망부탄 되고는 라고
거기서 그 럽체고 하고 도만 돼 유지자네 디데
So, am I right in thinking that when you send many, you get the pattern of the wave when the two slits are open? When you send few, you get a pattern of individual kind
That's
of,
right,
yeah,
yes.
like kind of particle.
Right.
So, in that case, can't we say that when many photons are collected, they behave like a wave?
And what do you say about the few ones? Do they also behave like a wave? At how many do you suggest the nature changes? Can the nature change if you have few or many? That's not possible.
두 그셀레나 자수스다 나라브레스야 타냐 자수스는 걸로 잡래
I can.
Can I try something here? Is this on? Make it on. If you send many particles through, you infer a wave. If you send a few particles through, you do not have enough knowledge to infer anything.
Not even as particles?
Well, they always arrive as particles. They always
Always.
arrive on the screen as a click. So they show up as particles. But the pattern is too ambiguous until you have many. Yeah? So you can't infer anything with certainty until you have
Can I
many.
give an example? Is this on?
Yeah.
A constellation. There's a constellation which we are all familiar with.
On
Suppose
Skype.
it's a very
Stars.
cloudy night and you can only see 2 stars. What constellation are you looking at? You don't know because you don't have enough stars to infer what you're seeing. This is one of the few things we've discussed that is not profound.
가르쳤어
호란사는 지라팅 사보게 말해서 그래서 그게 photon 그 간다 제 로즈 마당 봐도 니 웨이브 남주 튼다 라고 남주 튼다 그건 저바 제토야 그래요 말간 저바 제알이야
어다
시 차상
포른 찌기
라레 간다
그 속배선에 이 럽다
간다 방부터 하나 마도 니 라고 남주 튼그 매인자 니 라고 남주 튼레 두고 남주 레세제
Maybe Mambo's love the because Mambo Nyamda Tang Mare, ready Tangre.
Ready.
Karma goes ready like Karma cheeks you cigarette. Chick up. She's a goes to top of Chisoyagi catching in some mare. Palade do take it sober dog in some mare. Right, but not talking about the wave being like a sort of something that is made out of a collection of particles.
No, not at all.
One important thing
The
that
wave is assigned to each individual particle, but only as a probability. As a probability where it could show up.
But I think one of the issues that's important here, and I'd like to hear back, is in some ways it's the relationship between it's the role of causality in all of this. You see, because the pattern indicates some cause, some lawfulness, right? That lawfulness gives rise to the pattern that we see. But the individual events which comprise that overall pattern appear to be random. But how can a random set of events produce a lawful behavior? It seems to violate our sense of causality, that you normally think of you build up a form out of small causal events. But in this case, each of the individual events appears random, uncaused, if you will. But the overall pattern shows a very clear form which implies a causality or a lawfulness. Please, go ahead.
I'm getting confused.
I think not only you.
Welcome.
As you present it to a biologist, it really looks trivial and it sounds like an undersampling problem. Imagine that we have a wave, a periodic process, any sort of periodic process, which has peaks and troughs. And at the peaks, an event can occur or not. If you have only a few of these events disseminated over the periodicity, you will never ever find out that it is reflecting a wave process. It will look like Poisson if it's undersampled sufficiently. If you have on every cycle one without cycle skipping, you get a wave. It looks very nice. Haven't you got exactly the same problem? You have a carrier wave behind which you sample with your photons, but you undersample if you have only a few of these clicks. What's the problem?
The problem is not the inference of the wave pattern from a few or many. This is not the problem. The problem is if you have a certain if you can collect those particles individually. So you realize that they arrive as individual chunks, and very well localized chunks, each one. Now, how do you explain, if you want, how do you explain the pattern which you get as individual chunks which are which have been as localized along their trajectory as they are in the end? This is obviously not possible.
Yeah. So they have not been independent to begin with.
Sorry?
They have not been independent to begin with.
That we can disprove. That we can disprove. We can do this experiment with absolutely independent particles.
From different light sources.
From different sources,
which
completely independent.
Which don't produce waves, you mean?
Completely independent.
Oh, then they will still produce a wave.
They will still produce this pattern. They will still
still produce the wave pattern.
That was a discussion very early, that they may not be independent, they know from each other. Let's exclude it. They don't know. But maybe we should move on.
Yeah, I think we should.
The 초배돈 대신 접두가야 집게 pattern 없이 등교로와. 다 초바 좀 제기 두레톤에 대신 접두가라 아니야. 콜라 미생 해버스 매든이르지. 근데 그 randomness.
그게 몽고 스타인도 전에 쇼데 그게 패턴이 튼 거 봐.
네.
디 다야 그거래. 된대기 땅집에는 사몽고 제베이나 패턴이 집으로 튼 거래. 소수준 거래.
So when you have both slits open and you send many photons, you get this pattern. So do the same pattern occurs over and over again?
Yes.
Yeah, 다르죠. 다르시던 거죠.
if
it only depends on the color of the light you are using.
And the spacing between the slits.
And the spacing between the slits.
그준이 지고.
지고지. 다른 건다. 이 photon
사전 넘시라면 지고 얘는
the environment environment makes no difference like in climate and
no, that doesn't make a difference.
Nothing, yeah.
No. The same in Dharamsala and in Vienna. Doesn't make a difference.
숙제 정도는 개봐요. 그래서 또 수시 the frequency.
There's one
patterns had and the love patterns go.
Love patterns long.
The love patterns go to score.
비그래. 지난 랍 되게 온도가 가나.
This distance.
No, the pattern is on the back.
Pattern is
되게 그게 좀 지시죠. Patterns도 독시 국제이 될 수 있어요. 되게 no. The drawing.
Arthur, can you show the drawing that you had?
대도 무무스도.
네, so that's
the patterns 들보다.
네, patterns 랍 때 상만 돔. remember that the
top one has one slit open and the other slit is closed.
네. 저 부르등에도
That pattern is different. Bottom one, both slits are open, and you receive and you generate.
그 가참 주고. 나. 샴데 가참 주고.
그래.
다한테 찍도 가져다.
도서 질 두고. 그래.
아니 제도. 동당으로 제도.
당도다.
지기운지는 담으로 지기운이는 담으로.
당도 당사대도 찍은 찍어 봐. 기대 기운이 여러 봐.
그래. 그래서 그 주스면 아니요자.
주스면 아니요자.
좀 붙여주고.
나래. 때네 그 레레진 침배는 오늘은 저는 남주
그래서 말이잖아요.
말두드레 두고래. 두드레 두고래.
두드레 두고래. 지구도 가는 지구도 와는 지 이니 그 사이는 자는 지구 부부마 잡으시지.
나래.
그 도대가시. 그 기운이 있으셔.
나래. 이 기운이 요는 오늘은 지금도 도도진이 된 거야 저러 봐. 강대 도도지랑 찍던 봐. 또 어디 기군지잖아. 문제는 지나 기대 파동.
대한도 숨지 다 손질 잡을 해 못하나 그래.
No.
와다 시소도 숨도 제가 소리지. 그 손질 잡을 돼.
그래서 전체 잡을 때 있는 방법도 거 봐. So for example like I was suggesting that if it really behaves like a particle even when both slits are open, then we should observe only two bright spots.
That's exactly the point. That's exactly
and there
the
should
point.
be a big black band in the middle,
Right.
and then two bright spots.
Right.
That's not what happens.
That's not what
That's not
happens.
what
네,
happens.
대tin용도 거래. 이군이도
That's not what happens.
땅서드네 지금 땅 거로 봐.
Well, the two spots actually can overlap if you
다들
want.
네가 제샤요나 문제는 지나
They should overlap.
대 독도 직세 대 독도 직세 끼동 받침 보지 못하는 거예요, 뭐. 근데 디츠블이야.
근데 이거
이군이 있잖아.
근데 이거 숨 쉬어야 되는 가시도.
So what about if you have three slits?
Good question. Then this pattern gets a little bit more complicated. When you have three slits, what happens? That you get dark and bright spaces closer to each other. You get more of them.
랍도 충분히 망부시 있던
You
거죠.
get more of them. That's all. It's not very
패턴 찍어요, 그래서.
right.
되게 이 동야디 찍으래디 가서 정말 그도 찍으래디 얘네 그 먹었던 거죠 말이야.
장거리도 땅에 망부시 있던 거래. 땅들을 당겨 말아.
저 제대로 와. 저자가 찍지나는 친구 누구로.
그렇죠. 저 문제는 뒤치기나 저서 디니니마도 매자 디와잔 레시요 말아.
이게 다들 숙진시에서 그 찍고도 마셔지. 띄었어. 다 이거 풍부풍습 찍차서.
나래.
될 뒤숙인 거 안에 그 샴대 풍부 찍차야지. 뒤바슬라 니버지 용도 용쓰기로.
맞다. 니벌 레고 때 녀도 들어와.
맞다. 디니 바슬라 니버지 용도 말했어.
네.
그 대지 뽕사로 와.
나래.
두번 뽕붙이다.
나래.
뽕붙이 대지 차 차야 되잖아요. 그 대숙인 게 대 풍부 찍뽕마도 디니 빠라데 풍부 숨버지 뽕마도 용쓰기로. 그 이거 니부터 나와.
말단 딜레기요 말 딜레고 바로 레고 녀도 되네요 거로 봐.
dire.
저저는 디디도 디네고 디도 다 되네 내미션으로 되는지.
나래.
I think we
찍찍장이는 그 부부셔도 와.
나래.
단니 이번 인도산에 그 가참으로 와로.
나래.
가참에 왕께 두 번이도.
But we'd like to, in some ways, wrap up
Sure.
this part of the discussion.
Endless.
I have not made one important point yet.
Oh, yes.
You made many points, but one more important point. Okay.
And the important point is,
Finish on that.
Your Holiness asked whether it is independent of, the environment. And I said, yes, it's independent, which is not completely true. There is something, and that is now an important point. I could somehow, try to find out which of the two slits the photon really went.
The photon.
For example.
기본 디니나네 가기나네 침바이나스잖아.
Okay. This can be done, for example, by taking a small particle like an atom, or take one atom behind one slit, another atom behind the other slit, and see which of the two atoms gets kicked by the photon. Okay?
디 기본 디니 가네 침바이 마진 따제 제 두그레스 그래서나 기본 니자데 애톰레샤 엔페네 포톤 땅베나 니 기본 로스드네 그 애톰데 비제잡혀 그러면서 그 소전이다 가데니도 비제잡혀서 지금도 비제잡면은 비제잡었더니
Yes.
If I do that, then I know which of the two slits the photon went through.
Yes.
And the interference pattern disappears. And in general, whenever there is some interaction which allows me to conclude which of the slits the particle went, the interference pattern is gone. The stripes are gone. The stripes are only there if there is no information present anywhere in the universe which path the photon went through.
That's
Well, that's a little bit.
the 간다 기공 디니네 기공이 되잖아.
그래서
detected. So Rinpoche is asking, imagine if you set up this experiment in a kind of a new way. So instead of just a screen, you have a screen with, say, 1,000 mirrors, and you send photons one at a time. Will you see pattern? Will you see kind of pattern of the photons hitting each of the mirrors, or would you expect the same interference pattern?
Well, I still have to register the photon somehow. After the mirror, or what's the idea?
On the mirror.
Behind each mirror, I register the particle.
Yeah.
Yes, I would still see the same pattern. Right? Yes. Yes. Absolutely.
Kind of the Quran main point dirisha. Gigung ni chebeche. Ta gigung ni chebe tone gigung kane photon chimajin di 다시 제토야 네버 요레스. 대네 될 기용 거래로서는 독신 제자be 쉬고대 아니 갸고 인터페런스 잔통 말했어. 간다 기공 간에 치마진기 처바 제토야 그 experiment survey나 아니 갸도 인터페런스 하는 연구도
저거 거래.
디 인터페런스 같은 건 리모트 인터넷에 라고 남들 해야 돼.
지금 가도이네. 저처럼 대군 거기네 침배 레이스 디 셰나 되니 인터페런스 pattern 용 말해.
달라고 남기단.
마시나 인터페런스 pattern 용 그래.
잡으면 지소. 그냥 지소 주도 셰나 인지소 뭐로 같이지 지소 다리 앞도스 같이. 진짜 말아. 디 말은 자요시 같이.
I think the joke is entirely in Tibetan.
No, his audience was saying that this sounds a bit like the Samkhya. There is this notion of prakrit. Prakriti, it's generally translated as primal substance, and the world of kind of macroscopic world of experience is thought to be manifestations coming out of this primal substance, and liberation attains when the individual recognizes that all of this world of illusion is actually just an illusion coming out of the primal substance. And when you recognize this, the primal substance gets kind of embarrassed and dissolves all the manifestations. So this has a sort of a similar ring to this here. Because like when you can infer which slit it went through, then the interference pattern sort of,
disappears.
Sounds like the collapse of the wave packet in the primal substance. Yeah,
I think this is a perfect place to have a tea break. Find some primal substance down where we have tea, and we'll come back to these kinds of ultimate questions about the nature of reality after the tea break. Thank you very much. 15 minutes or so, come back at 2:30.
Very good.
Thank you.
Conversation, and I'm sorry that we don't speak Tibetan so that we could have also heard all of the details of your conversations with each other. But it was wonderful.
I don't understand fully about the English.
Yeah.
So same.
Now we're even with regards to that. If I might, I'd just like to say a few words about why is this important? Why is what Anton ordered universe, where the objects of that universe were well described by classical concepts. Around 1900, 1905, 1910, in that period, these experiments began to show that very simple elementary phenomena led to conflicting conceptual understandings of the world around us that are very fundamental. That the simple picture of reality which we had prior to 1900 simply is no longer correct at a fundamental level. At a large level, at a gross scale, most of these effects disappear. But when one looks with great precision and great subtlety then the nature of reality itself is called into question in a fundamental way in quantum mechanics. There is a new kind of order that is there. It's not that one goes from an ordered universe, a classical universe, to a chaotic and disordered universe. But the order arises, you might say, in a new and more subtle way. And in point of fact, this is a good segue to, I think, what Anton's going to be speaking about now, where you could say we have begun to realize the full power of this new understanding of reality. In the beginning, it was thought that the classical world gave way to this rather exotic and, in some sense, irrelevant world of microscopic atoms, photons, and such like, and that there wasn't a real power or real usefulness to this. But we now understand that indeed this is a resource, this is a new basis for technology, which gives us a whole new set of tools that is just now, in the last few years, being developed. So you have a new picture of reality, and 100 years after that, a whole new set of technologies which are making their way into our lives based on that very subtle and very different understanding of reality. I don't know, Anton, if I did justice to...
Yes, thank you. Very good.
Okay.
And I would like to add one point which is very important to me. To me, it connects to what John said in the beginning. You asked about this question, what is the reason why scientists are here? What do I, as a scientist, want to get out of the discussion? And the point is that from a conceptual, I mean, we can very well handle this kind of paradoxical situations we have been talking about mathematically, and we can confirm them in experiment with very high precision. But we still do not know conceptually what is going on. Why is the world so strange? And what I want to see someday before I pass away, that someone explains to me why it is so strange. So I want to learn new concepts, and this is a place, and there were some new concepts brought out in your discussion, which are very interesting for me, and where I have to think more, and where I hope I learn something which might even have relevance in helping to understand some of these phenomena in physics. So that's my reason, because John asked the question. So it's about concepts. Concepts, new ideas, they can never come out of the traditional which you know already. They have to come from somewhere completely different.
And
maybe
I think
they can come from here.
Yeah, and I think just a little sort of sidebar with regards to the kind of lively, even chaotic discussion that took place. And it's because of that conceptual openness. If Anton had come with a fixed set of concepts concerning these phenomena, it would have been very clear, very tidy, a kind of ordinary presentation. But what he put forward was something actually we don't fully understand. We can technically work with the field, but the concepts are not developed. And this is something which the greatest physicists have basically reached a consensus on. We do not understand.
And I was smiling actually when this discussion started between Your Holiness and your friends here and your friends there. So I was smiling because this is exactly the climate of discussion among the physicists in my group. It's exactly the same. It's exactly the same. Openness, and ask everyone.
It's a research
Ask
community.
the young ones. It's a method of research. Ask the young ones also. Not just the old guys who are supposedly very wise and knowledgeable. Ask also the young ones. Maybe the youngest one has a great idea, you know. Okay, so maybe we should. Right.
All right.
Maybe I will now come to a little bit of technical things, but it will immediately become conceptual again, as you realize. Now, as I mentioned, one of the big changes in the last 10 years since we met last time is that there's a new technology evolving where these quantum phenomena are actually applied, the quantum behavior of individual particles. And it turns out...
technology developed to more. This word. Classes. Classics quantum probably tatan kewa shuju in das mambuchi tatan quantum gti chitame gan to nyodo tambul langbo zamma to zawe chita telia penu chita metaver zigores tata chalia quantum tatan shilishaje and chuje soyon dugala and gongone dane His Holiness is curious because, when we're talking about quantum level, we're talking at a very, subatomic particle level reality. How can you build a technology based on that?
His Holiness has actually seen that. Right.
Yes.
This was when you were in Innsbruck.
Yes, that's right.
And you saw how we, for example, send individual photons. If you remember, you saw how we send individual photons through glass fibers through a tunnel. Remember that?
Yes,
in
that's
Innsbruck? And this kind of experiment at that time was just experiment to test how strange these things are. Like, if you remember, for example, these quantum correlations I mentioned, this entanglement. It's also in your book where observation of one system influences the other one instantly. Of one photon influences the other one instantly. And this kind of experiment...
So this is the phenomenon we're talking about, where there is a correlation, but there is no communication, and you can determine by checking one behavior, infer the other.
Well, the deeper point is you measure one,
and then you get the information.
It gives you a random result, as far as we know. Randomness is a special issue, I know. And this measurement not only forces this one particle to give you some random result, it also forces the other one, no matter how far it is away, to give a distinct result. And this kind of correlation can now be used to transfer information. That's part of the game.
Really? Wow.
Okay, you'll see.
The correlation, the shilishaja information parts down towards. I think understand.
We'll see.
Okay. We'll see. Let's keep going slowly here. A basic notion here is the notion of a bit versus what is called qubit. Qubit is quantum bit. Okay.
It's a new term,
New term.
Qubit is a new bit is well known. Bit is where every computer is based on bits. For example, in the computer, bits are electric pulses, and they are 0 or 1. In every computer, every information is represented as bits. Be it language, be it a picture, whatever. Here is a classical bit on that picture. This is a switch. In principle, you could build a computer using such switches, which actually has been done. The first computers were built using electric relays, electric switches. Now, in such a physical bit is 0 when for example, when the switch is off. It's 1 when the switch is on. It's very easy. It's not a complicated concept. The quantum bit is something new. So the bit is 0 or 1. The quantum bit is something new. You see, This thing, I mean, it's an illegal picture. This bit here is in a superposition of 0 and 1.
It's a trick.
It's a trick. It's the same kind of trick which my photon did in the earlier experiments, in a sense of going through both slits at the same time. We call this superposition, being 0 and 1 at the same time. We call this Cupid. I apologize for the equation down here. It's the only equation which I show. And it simply says that this system now is in the state 0 and in the state 1 at the same time, which is something a classical bit cannot be, and which in itself you can feel already has much more richness to it than being just either this or this. If it can be both at the same time, and if you build a computer out of these elements, you can have much more information handled than with the classical computer.
The classical laws which on off the only number tangpute off the number 0 tevena the yana only na number tangpute off in number 0 no off kuning eba chenba niga tuchi yo maro the quantum can let you gala niga himbe much shagi or superposition shan to gala ni switch the number tangpute niga res the on the off niga res labje niga himbe shiduji shaje don't tension thing georo the superposition thing to go punsum jileje and the shilishaja any computer sort of works. So this is the base of quantum computer?
This is the most elementary element of a quantum computer. Quantum computers is then built out of, is not switches like that. It's atoms or photons or electrons. But the common feature is that they are in the superposition of two possibilities, and therefore they can contain much more information than a classical computer, which can only be this or this.
So you only have the superposition basis, no, you don't have all three.
You have actually much more than what I show you here.
Okay.
You can have 0,
1,
you
or
can
superposition.
have 1, you can have superposition of equal amounts of 0 and 1, which points to the side. But you can have a little more 0, you can have a little more 1 if you want. So it's a whole rich possibility of storing a lot of information in this whole system.
찹샤로 제가 처음에
나.
디디스는 찹샤 제도하면 다 찹샤지. 땡큐 개그맨 찹소.
So then that means you can have no determined states.
That's exactly the point.
So on that basis, how can you have a machine that needs determinate responses?
Yes.
Like a machine, like a motor.
That's a great
question. Right. You know, we say it's a great question if this is the question you are hoping to get, because then we can say what's actually happening here. There are two answers. First answer is that this system here gives you a non-deterministic answer if you ask it, are you 0 or are you 1? Okay. But it gives you a deterministic answer if you ask you, are you 0 plus 1? So there are certain questions which the system can answer deterministically. That's one point. The second point is...
basis indeterminate. No. Can you repeat that last bit?
The last bit is...
the
last bit is, you know, I can ask my Cupid many questions. Asking means I do an experiment. One question could be the question, are you 0 or 1?
Yeah.
So if it is spin, you are familiar with spin because you were using your fingers like that. Are you 0 or are you 1? I can ask that question. If I ask my Cupid that question, then I get a random answer, a non-deterministic answer.
No.
We have ways to correct for that. I will mention that in a minute. Second point is, I can also ask it another question. Instead of asking, are you 0 or 1? I can ask you, are you 0 plus 1, just the way it's written down here? And then the Cupid will deterministically say, yes. So there are situations where you get deterministic answers. And and obviously the whole space of possibilities is much richer.
Mm-hmm. You're in a quantum
of
state.
Possible answers.
Yeah, you're in a quantum state. If you ask a classical question, then you reduce that richness to a simplicity. If, on the other hand, you find a way to pose the quantum question and get a quantum answer, then it can give you a deterministic answer.
Yeah, but it still doesn't respond to His Holiness's question. His Holiness's question is that when you use the machine, say for example, like you have to switch on the motor based on the quantum machine, then unless you get a determinate response that will, when you want to switch on the engine, it has to switch it on.
Right.
Right.
You have a very different interior to the machine, you could say. The motor of the engine, in the case of the quantum computer, is quite different. The states of the interior are ambiguous in the way that is described here. They don't have a cycle where in the normal computer, you'd start with one deterministic state, and then you go to the next deterministic state, and to the next deterministic state. In this case, there's an evolution, but in this quantum richness, with this quantum ambiguity. And picking up on the theme of measurement that you said last time, when you remember the double slit, when you measured, it ruined everything. If you do the same here, it ruins the computation. The machine will crash if you look inside, right? So you have to allow the ambiguity
the primal substance. The primal substance.
Right.
Let me make...
machine the machine to come on go.
Sorry?
When you say one, you ask it, are you 1 plus 0? Do you really mean that? To what degree are you 1 and to what degree are you 0? And you get a deterministic answer?
No. I ask, are you 1 plus 0?
In the sense of a superposition, not are you.
Are you in the quantum
but
state?
Would that be true for every?
And that's what we have learned. We have learned to ask these quantum questions now in experiment.
All right.
You always say yes.
Yeah, you'd always say yes in that case. Why? That's not any information.
In that case, it will, in this simple Cupid I showed you, will say yes.
Always.
But it could be that this Cupid is the consequence of a long calculational evolution where you don't know yet what it is, and then you ask.
Right.
And then you get some new information.
Right.
Here it's trivial. Here it's trivial, because here you know what it is.
Could I make a comment here?
Yes, sir.
I want to make sure I understand your question. I have a box, which I can't see inside the box, and there's a blue golf ball and a white golf ball, and one of those two balls is in the box, but I don't know which. So I could interrogate the box and say, are you blue or white? And I could look inside and find out. Is that the kind of a thing you're thinking of? For example, if there was one ball in the box and you said, are you blue and white? Well, the answer to that is yes. Is that the way you're thinking?
Well,
Because if it is, it's definitely not the way Anton's thinking.
Yeah, no, it seems to me that Anton is saying that in the box, if you ask the box, are you a locus of either blue or white, or both blue and white, without trying to make the deterministic, classical answer, you are either blue or white.
Exactly.
But if you ask, are you a locus of both blue and white, then the answer would be yes. And maybe it's just because of the product of the particular example you chose. In that particular example, obviously the answer is always yes, which doesn't you can't encode any information if the answer is always yes. But you're saying that this would be a small unit in a much larger system.
Right.
Okay.
That's right.
So it's really the kinds of questions you ask. You can interrogate more complicated states than simply a binary state. Is the point?
Right.
Okay.
Right. Actually, right. In each qubit, in each bit, I can only encode one piece of information, yes or no, to a certain question. Is it raining or is it not raining? If it's raining, it's 1. If it's not raining, it's 0. In a qubit, I can encode an infinite amount of information. And that's because you can take different amounts of zeros and 1. And that's the richness. And the big trick is, if you do a calculation with your computer, which question to answer in the end, such that you don't run into the randomness problem. That's a serious research program, but people have found ways to answer that. So your point is well taken. You're absolutely right. Completely correct.
The information storage now don't get shit. The bit now on the off 1 to 0 to say the machine computer language computer software program 010 and then analog. But this is the digital, basically 01.
Yes, digital is 01,
right.
and in the case of the quantum qubits, you have what looks like a 0 and a 1, but you can prepare these superposed states, which give the richness that you're talking about, and then you're going to talk about an entanglement.
And the suggestion here is that it can contain a lot more information because of that flexibility.
That's the
yes or no,
more possibilities.
알레 다 해지요. 가사 주디. 유기 체벌하다 시기 무슨 말다.
나.
따라 가서 그래. 도미시베 그거다. 유를 가서 그래. dum주.
나는 dum주다 맞지.
유기 체벌 해지지 시행을 가서 지고 말다.
나는 간데스 지금 나노. His Holiness is wondering because again comparing to the kind of Buddhist epistemological distinction between how thoughts and conceptual thoughts work by means of exclusion and selection, and they select properties one at a time and engage with the object, whereas experience or perceptual experience is thought to be much more encompassing, can contain a lot more information. So he's wondering whether that is a parallel.
All information
so the quantum approach would be ability to capture all the information. Is that the idea? Whereas the non-quantum would be kind of a selective approach. By selecting one, you exclude the other.
Yeah,
there is a quantum holism which is characteristic. I think you're going to talk about, right?
I think we should mention that right away here.
Yeah.
That's the right thing. I think that connects to exactly this question now. There is a beautiful novel, a beautiful story by the Argentinian writer Jorge Luis Borges. Borges wrote a novel which is called The Infinite Library, or in some languages is called the Library of Babylon. It's a library which contains all books which have ever been written and all books which will ever be written. Okay? How is that possible? Now it's easily possible because you print books with all possible combinations of letters.
So isn't that in that case it's already been done since ever since the letter was invented? All possible combinations have been used.
No, I mean your book, the World in a Single Atom, is a new combination of letters, which has not been used before. I use all letters, all letters which I need to write down. Each book is a specific sequence of letters.
So then how can you have a library that has all the books that will be written in the future?
Well, because
not yet materialized.
Because you just start with all possibilities. The first letter is you start with A. The second one A, second one A. Next book is AAB. Next one is AAC, and so on. All combinations. Right? Now, Borges himself realizes that such a library is not very useful. Because how do you find the right book? How do you find, for example, the world in a single atom by His Holiness the Dalai Lama? Because this library contains the world, the universe in a single atom. It also contains the universe in a single atom with all possible single misprints, with all possible 2 misprints, 3, 4, and so on. So it's not a very useful library. And it turns
중국이 대비전하는 상대 열쇠도 근처서 싸움 같다.
이게 뜻한 거잖아요. 섬당 거래. 이게 뜻한 거잖아요. 나래 내가 스케임도
가다변은 가서 비유를 시키면은 양도 세지 뒤뒤 지금 맞도 야야 말이야. 대비 인시전.
근데 딕단이야. 가탕 볼샤지 딕지야. 가가가가스야. 딕단지.
And you know, there is actually mathematicians who can prove that you would expect that anyway, that if you want to have a certain book, is much more work to find it in that library than to write it yourself.
Now,
this is just the story of Borges, a beautiful novel. Now, the big news is that in quantum mechanics we can actually can have one book which contains all possible books. It's not a library, it is one book which contains all possible books.
Yes.
And I now want to explain briefly how this book works. In this book, the information is written down in, you guess it, qubits, in quantum bits. It's not written in bits, in qubits. And furthermore, these qubits are all entangled with each other. Entanglement means, in your book, Your Holiness talk about entanglement between 2 particles. Now in this book I have 100,000 or 200,000 or whatever letters it takes to write a book of qubits all entangled with each other. Which simply means that just like in the 2-particle case, it meant that when I look at one, I do a measurement, I influence the other one. Now, this is a picture which tries to indicate the entanglement of many qubits. Each blue point is supposedly to be a qubit, and you have many connections here. Now, if I measure 1 qubit, then it changes the whole state. It does not only change the one I look at, it changes all the other ones. Then I measure another one, not the one first, another qubit, and that changes the rest. And I keep going. And if I keep going the right way, in the end, I have the book I want. So,
if you type the first sentence of His Holiness's book, 1 letter at a time, gradually you'll collapse the whole book.
Right.
You'll pull that whole book out of the library.
So this is one book which contains all possible books because of quantum superposition and because of entanglement. This is meant, and this is not just. This is not just fantasy. This is reality. You know, I mean, we do experiments not with 100,000, but with a few qubits. But this is really a technology which is now being developed.
The superposition information store. Is it because the superposition allows you to?
Wolf has a comment. Go ahead, finish.
Is it because the superposition allows you a much greater capacity for storage?
That's right.
And then the entanglement provides you that if you get the first thing right, because they're all entangled, you will get the others.
You collapse the others. Yeah.
Is that the idea?
These are the two essential points.
But then how can you
Absolutely correct.
But how much do you have to get to, get the rest of the book out?
Well, the point actually is as always, a little bit more complicated. The point is that there are two things. The way Arthur presented it was a way to visualize it nicely. But what really happens when I measure one qubit, I take it out of the entangled state. It's the rest which I drive somewhere. First point. Second point, you were quite right in saying if I have this entangled state and if I get the right measurement, then I can proceed. The right result. Now, in quantum mechanics, we have this silly randomness, so we don't know actually whether we get the right result or the wrong one. And in half of the cases, we get the wrong one. Now, the real trick now is, and that's a great discovery, not made by us, it's a great discovery, that if you change the future measurement, depending on the result you get earlier, you can correct for that randomness. Okay? And you can make the whole thing deterministic. And you make a certain number of measurements, and then the qubits which are left over are the information which you want.
Go ahead, Wolf. Yeah.
It then functions like the brain, like an associative memory, where you have
like what?
An
associative memory, where you have a virtually infinite storage capacity, as we know our brain has, with all the pictures that you have seen throughout your life, and you have a few anchor points, and then the whole thing comes out. You pull it out. You don't have to do a serial search. You find out of the mess immediately what you need with a few cues. Sounds very, very similar.
Yeah, this raises another, I think, related point that for me is in quantum computation and these sorts of problems important, and that is that one of the models that we have for the brain or for the way we process information, the way we think, is the classical computer. Right, and it's far too limiting. And here is a technology which is actually being developed, which is quite detailed, explicit, actualized to a certain scale, which has a very different, as it were, metaphorical or quality about it. And it opens up a completely different conceptual understanding. When you were speaking about how perception works versus, say, a linear concatenation of thoughts, it's very different. One's proceeding holistically in a certain sense and associatively in one case, and one is proceeding in a very methodical and linear way. Both are valuable, both are proper, but if you think you only have one type of thinking, you've limited far too narrowly. So here you have a case in quantum physics of a now actual technology, the quantum computer, which has a very different modality for computation. It proceeds by holes, and then you, as it were, work from that holes through, as it were, moving in through these defining elements. That refines the calculation, and in some cases it gets extraordinary speed up, extraordinary, much, much faster kinds of computation.
No, that's the niga yimbe shi dun delia rigdam dam bu sha tu yo anza information juya.
Oh yeah.
Such a gores storage capacity shukchim digal da ko de get some entangled just pension dewe bu janya yinza then ni man du ni du ji kap pen tang back up ya dewe de ni ka tang back up jik da du go jik choba che tu gor ba dinan sing du mang bu entangled che tu benas the quantum than qubits mang bu entangled che tu bena and qubit jig to le measurement che ta che che bin du kala and qubit shanda na information de get ne choba che tu yo res den de ko ne ani now
interview. Prepare for tomorrow.
Okay. So this was just a small glimpse into one technology which is evolving now, which is really exciting. Maybe I want to.
But are there
mention
really computers like this?
Sorry?
Are there actual computers
Well,
like this?
so far we have the status is that this is as I mentioned a big worldwide program. You know, there are countries like Australia or even China, for example, are putting $100-200 million a year into this kind of research. Mm-hmm. So this is really a big thing.
Can you say
and
what it's being applied to now? What areas are the most?
Well, it is not being applied yet. We are in the stage of developing the hardware. Where we stand is at the very beginning. We are able to have small quantum computers, which consists of 4, maybe 8 qubits only, which is much too small to do anything real. Okay, so it's like in the early days of computation, we are simply developing the elementary elements and showing how we can put them together.
So in a way, there's a kind of a blueprint is done.
Already.
It's more of a development now.
It's a development, but there are very big challenges. Very big challenges in terms of the development, but we are in the development stage.
But it's important also to say that mathematicians, theorists have proved that certain kinds of problems, mathematical problems, which are impossible or nearly impossible, very, very difficult, become very simple using a quantum computer. So you have a theory which says if you can build a quantum computer, then a class of problems which have been intractable now can be simply solved. And in particular, the ones that are most, you might say, I was going to say sexiest, but that's probably not the right thing to say here. The ones that have the most excitement is the factoring of large numbers. That is to say, you take a very large number and you find its prime factors. And that's used to transmit secure information, secrets, financial information. And that code, all of those secret codes can be broken using a quantum computer.
computer nane hack che kuma jabal ya ngel the somewhere code the chugurba code the raka bushi buchi work so ang che to bushi buchi dabi onduga now.
Martha, did you have a comment?
Yes, well, more of a question. I'm struggling to understand this. From what you've told us so far, there seems to be a free lunch being had here. You type in the first 2 sentences of, the universe in a single atom, and you get the whole book. Somebody, before you got there and typed in the first 2 sentences, somebody had to set up the entanglements just right. Is that true? I mean, in analogy with Wolf's comment, you need the right pattern of synaptic connections to make the network go into the right attractor state. So how do you program these nets, and can they learn?
Thank you very much for that question, because that is extremely important. The point is that this initial state is the same for every problem you want to solve. It's a universal state. So the state is exactly the same for any so it carries no specific information. The only interesting thing is the connectedness among each other, and that is universal. And the program you were mentioning the word programming. The program is now something very different compared to a program in the usual computer. The program is the specific measurement sequence which you have to use. And that specific measurement sequence forces these qubits, which initially did not carry information, forces them to evolve towards carrying just the right information, which is the solution of the problem which you want to solve. And that's really fantastic. This is a completely new way of thinking about computation. It's different from any any computation people have been talking about so far.
Up till
Completely
now,
different. It's something absolutely new.
right. Up till now, everything has been built up piece by piece, bit by bit. Here, you're working. The whole part relationships are quite different. Right? Through this massive entangled state, there's a kind of quantum holism, as it's called. And what you have to learn to do is to exploit that quantum holism. And this is a very rapidly evolving field. People are discovering new ways of working with that quantum holism, deepening it, texturing it, and new possibilities emerge, surprising ones. We've thought for so many hundreds of years of building step by step, increment by increment, but this is now coming at it from the opposite side. Create this universal state which is massively entangled, which is a whole, and then work your way in through measurements to, as it were, break it up into a specific. Okay? So you don't build a specific out of parts, you start with a whole and then condense the specific out of the whole.
So in a sense, it's the first technical application of wholeness,
Right.
It's really interesting.
How do you develop the rules for determining the measurement sequence?
Well, that's a very good question. It has not been solved for many problems so far.
That's the programming question. How do you program this device?
There is a general theorem. There's a general theorem that this kind of computer is equivalent to all classical computers, so it can do everything a classical computer can do, and it can do everything a conventional quantum computer can do, which is something different than this. So these theorems exist. How to find the program in a specific case is probably as much a creative procedure as it is in programming a standard computer. You have to be clever to do it the right way.
But there's a set of problems which have been solved, which are of extraordinary value, where we know the result. We've been able to prove those theorems. You understand the question?
It's a very good question, yeah. It's a very good question. My feeling is that the answer is it can do much more, but there's no... there's a proof that it can solve problems which a classical computer cannot solve within the time of the universe. There are proofs like that exist for certain problems. So it can do more.
You're talking more in terms of calculation problems.
Calculation problems which are so lengthy that it would take so many times the lifetime of the universe. In the case of a quantum computer, we don't yet have one, but if it was a proper quantum computer, it would happen very quickly. And that's part of the reason so much money is going into the project, because it's so powerful. It allows us to solve problems which we really would like to solve, including Defense Department kind of problems, unfortunately. But we are already at the end of our time. I'd just like to summarize a little bit of what we've been trying to do. I spoke at the outset of this session concerning, you could say, this new understanding of reality, or the abandoning of a classical picture and the arising of a much more subtle and difficult engagement with the quantum phenomena and quantum level of reality. How do we understand the nature of the world? And this is one of the key problems that Your Holiness has been interested in. I think with regards to the quantum computer, qubits, and all the rest, what this shows is that our understandings in terms of parts and wholes has also been too limited. And that we have, as Anton said, the first technological applications of true holism. Up until this time, it's been kind of a metaphor that there are wholes, and it seems to me it's always been very vague. But now there is actually a mathematics and a technology of holism. What are the implications of that for our understanding of the world? This interconnectedness that Your Holiness is always speaking of. This is a completely interconnected state where all the possible you might say, states are densely connected, and all possible and potential past and futures are there. I mean, it's a rich field of interconnectedness. And it's not just an abstract concept or a theoretical concept. This is something now which Anton builds in his laboratories, which will be sold at some point in the future in your stores, that we will use that kind of interconnectedness as part of our daily lives. So we tend to think of ourselves as built up bit by bit, and now we have qubit by qubit, entangled to create these wholes. To me, this is a very powerful and inspiring idea, a picture based on what we know about physics, not just speculation, what we know about physics, that has big philosophical implications. We're going to pick up with quantum physics tomorrow morning. I know you're all going to be looking forward to that. But tomorrow morning we'll continue with some more elements out of quantum physics. And in particular, what we'd like to do is to invite a couple of Buddhist voices to come to speak to us about relational ontology, natures of causality, as they connect to some of these ideas. We'll probably lead off a little bit with some physics concerning causality and randomness, and then a look at the ideas of causality in Buddhist thought, following on with also something concerning relational ontology. So thank you once again, Your Holiness, for your time with us. We hope this has been instructive to you.